Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight, we're stepping into one of the strangest corners of reality, a place where cause and effect don't always shake hands, and the universe seems to change its mind the moment you look at it. This is a calm journey through quantum paradoxes, the kind that make even physicists lose sleep. But before you settle in, if you enjoy these gentle explorations, you can like the video or subscribe, only if you truly want to join us again. And when you're ready, leave a little note below. Tell me where in the world you're listening from and what time it is there. It's always comforting to imagine all of us scattered across the planet, sharing this same quiet moment together. So if you're ready, dim the lights, let your shoulders fall, and take a slow breath. Tonight, we'll look closely at the cracks in the story we tell ourselves about reality. For most of your life, the world feels steady. You drop a glass, it falls. You turn off the lights, the room becomes dark. It's simple, predictable, reassuring. One thing follows another, a tidy chain of events that feels solid enough to stand on. The floor beneath your feet, the sound of your own breath, the glow of a lamp, all of it seems to obey the same reliable rhythm. But sometimes, if you look too closely, something begins to shimmer at the edges. Small things start to behave in ways that make no sense. An electron vanishes and reappears somewhere else. A photon travels two paths at once. Experiments whisper that what happens now might depend on what someone decides later. It sounds impossible, but these aren't mistakes or illusions. They are real, repeatable results. They've been tested, verified, and still they make even the calmest minds uneasy. When you hear the word paradox, you might think of riddles or puzzles, strange but harmless ideas that tie language into knots. But in physics, a paradox isn't a clever trick. It's a wound in understanding, a place where logic bleeds. Classical physics, the world of falling apples and spinning planets, has no such wounds. In that world, every event has a reason, and every reason leads to a result. But when we peer into the small, the invisible, that tidy certainty breaks. The deeper we look into atoms, electrons, and light itself, the less the world behaves like a well-built clock and more like a whispering sea of possibilities. This was the birth of quantum mechanics, a theory that doesn't predict what will happen, but rather how likely it is to happen. It doesn't promise certainty, only chances, and yet somehow it works. It powers everything from computers and lasers to medical imaging and GPS satellites. Quantum theory builds the modern world, even though no one fully agrees on what it actually means. It's like having a book that tells you every page number perfectly, but refuses to explain the story. The equations describe what particles do, but not what they are. That's where paradoxes step in. They aren't side effects or curiosities, they're signposts pointing to something missing in our picture. Imagine your phone works perfectly, calls, texts, everything, but once in a while, the screen flashes with strange symbols you can't explain. It still works, but you can't shake the feeling that something important is happening beneath the surface. That's what quantum paradoxes are. Little flashes from a universe we don't yet understand. At the centre of all these riddles lies a single question. What does it mean to measure something? In our everyday lives, measurement feels simple. You look, you count, you check. But in quantum physics, the act of observing doesn't just reveal, it decides. Before measurement, a particle can exist in many places at once, a soft blur of possibilities. But when we measure, the blur vanishes, leaving only one outcome. The question that haunts physicists is, why? What causes this collapse of maybes into one solid fact? Is it the measuring device, the human mind? Or does the universe itself somehow know when it's being watched? The more we try to answer, the stranger the questions become. Some experiments show particles that seem to choose their path only after we look. Others suggest that the future might quietly influence the past. There are setups where two observers record entirely different realities, and both are correct within their own view. It's as if reality has become something elastic, stretching and twisting depending on how it's seen. And yet, the math remains perfect. The predictions hold, the phones still ring, the lasers still shine, the science works, the story doesn't. Quantum mechanics gives us results, not reasons. It's like a beautifully tuned instrument that plays every note precisely right, even though no one understands the song. The giants of physics felt this discomfort deeply. Richard Feynman once admitted, "Nobody understands quantum mechanics." Niels Bohr, one of its founders, said that if you aren't shocked by it, you haven't understood it at all. Einstein called it the end of physics as a true science, if it were correct. Schrödinger, whose equations made it possible, confessed he wished he'd never started down this path. These were not careless minds. They were the people who built the modern universe, yet they all felt uneasy, as if they'd opened a door that led into fog. That's what makes these paradoxes powerful. They are not dead ends, they're questions that glow in the dark, showing us where our understanding frays. They remind us that the solid ground beneath our theories might be thinner than we thought. Every paradox is a mirror, showing both our brilliance and our blindness. They're not signs that the universe is broken, but that we might be asking the wrong questions. So tonight, we'll wander through that fog together. We'll explore the strange experiments where light seems to choose its history, where two people can see different truths, where time bends both ways, and where reality itself behaves like a story still being written. Each paradox is a little window into how much we don't know, and how beautiful that not knowing can be. If you listen closely, you might notice that what sounds like chaos begins to take a shape of its own, a quiet pattern that says something simple. The universe works, but we still don't know why, and maybe that's exactly what makes it worth listening to. As we drift deeper into the story, the next step of our journey will follow a single thread. The question of why these paradoxes exist at all, and what they're trying to tell us about the limits of what we can know. Imagine standing beside a still lake at dawn. The air is cold enough to quiet everything except the faint sound of ripples against the shore. If you toss a stone into the water, you can predict exactly what will happen. Circles spread outward in perfect rings, one after another, fading with time. This is how we expect the world to behave. Steady, logical, repeating itself the same way every time. It's how our minds find comfort. Cause, then effect. But in the realm of the very small, that certainty begins to dissolve. When the stone you toss is no longer a stone but a single particle, like an electron or a photon, those ripples don't behave. They fold in on themselves, split, overlap, and then vanish, as though they were never real in the first place. That's where quantum mechanics enters. A theory built not on certainty, but on possibility. It doesn't say, "This will happen." It whispers, "This might." The world it describes isn't made of fixed points, but of shifting probabilities, like countless tiny coins all spinning at once, waiting for the moment one lands heads or tails. The equations of quantum physics let scientists predict the odds of each outcome with astonishing accuracy. They can tell you the chance of an electron being in one place or another, of a photon striking a screen in just the right spot. But they cannot tell you why one particular outcome happens when it finally does. It's a strange kind of success. So accurate it feels like magic, and yet so incomplete it feels hollow. In our everyday sense of logic, understanding means knowing why. But quantum physics teaches us that prediction might be the best we can do. The universe plays a melody we can follow perfectly, yet we have no idea what instrument is playing it. This is the quiet contradiction at the heart of modern science. Quantum mechanics works. It has never failed an experiment, never given a wrong number. Our computers, our satellites, the semiconductors in your phone, all of them depend on it. And yet, Ask even the most brilliant physicist what it all means, and they will pause. They might smile, shrug, or tell you that meaning is not part of the equation. Because in this world, meaning itself seems to shift, just like everything else. If we follow this thread a little further, we find that what quantum mechanics offers is a kind of statistical poetry. It describes waves of possibility flowing through the universe, overlapping, merging, and fading into certainty the moment we observe them. The wave itself, the mathematical description, is called a wave function, but you can think of it more softly, like a fog of potential. Every particle is hidden within this fog, existing everywhere it could be until something disturbs it. Then the fog condenses into a single drop of dew, one location, one result. Scientists call this collapse, but we might think of it as the moment the universe makes up its mind. The strange part is that we never see the fog directly. We only see the dew after it has formed. Before that, all we can do is imagine the haze of possibility and write down numbers that tell us how thick it might be here or there. In this way, quantum physics doesn't describe reality as it is, but as a set of chances waiting to be revealed. This feels deeply unsettling because it challenges something we've always believed about science, that the world exists in definite ways, whether or not anyone is watching. Newton's apple fell whether there was a physicist beneath the tree or not. But in the quantum world, that simple idea begins to blur. A particle doesn't seem to have a location or a spin or an energy until it is observed. Until that moment, it carries all possibilities within it, like an unopened letter that contains every answer at once, waiting for you to decide which question you are really asking. You can picture this as a kind of conversation between us and the universe. When we measure something, we aren't simply listening, we're speaking too. Our act of asking seems to shape the answer that comes back. It's not that we control reality, but that we participate in it more intimately than we ever imagined. The observer and the observed are no longer two separate things. They form a duet, each note influencing the other. And so, physics becomes something more human than it ever meant to be. It becomes not just the study of matter, but of how matter and mind meet. Every observation is like opening a small window in the fog, but the act of opening it changes the shape of the fog itself. If you try to look too closely, the fog resists. It pulls back, reminding you that precision has a price. The more clearly you know one thing, the less clearly you can know another. That is the heart of the uncertainty principle. But rather than thinking of it as a limitation, perhaps it's a kind of protection, a reminder that mystery is part of balance. The universe doesn't want to be cornered, it wants to be explored. To live in this probabilistic world is to accept that knowledge is no longer about control, but about harmony. The equations give us predictions that work to the 15th decimal place, yet they leave us with questions that science alone can't settle. Why does probability exist at all? Why does observation change what's real? Why does the universe, when left alone, seem to hum with every possibility, and yet when seen, freezes into one? Physicists have built countless interpretations to explain this. Many worlds, hidden variables, objective collapse. But none can claim the final word. It's as though the truth is a prism, and each interpretation catches a different colour of its light. We see fragments, never the full spectrum. But maybe that's all right. Maybe understanding the universe doesn't mean stripping it bare, but learning to listen to its music without needing every note explained. There's a kind of peace in that. When you stand by that same still lake and watch the ripples fade, you don't need to know the exact equation of motion to feel their beauty. You just watch the patterns, spread, disappearing quietly into the morning mist. And so quantum physics in all its strangeness brings us closer to something ancient, the awareness that mystery and order can live side by side, that we can build machines with flawless precision and still admit that we don't truly understand the reality they rest upon. The paradox is not a failure, It's a mirror showing us that understanding isn't always about removing uncertainty. It's about learning to live gracefully with it. If we continue along this path, we'll begin to see how these paradoxes aren't just oddities of light or electrons. They touch something deeper: time, causality, and even what it means for something to exist. The trail of clues now leads us gently toward the first of these riddles, one so quiet it almost feels like a trick of light, the experiment where photons seem to decide their own past. If you've ever stood in front of a mirror and looked deeply into your own reflection, you might have noticed something subtle. The moment you start focusing on your eyes, the rest of your face blurs. When you shift your gaze to your mouth, the eyes soften again. You can't capture the whole image at once. Attention itself seems to sculpt what you see. Something like that happens in the quantum world. To look is to shape. To measure is to make. In classical science, measurement feels neutral. A thermometer doesn't change the temperature. A ruler doesn't alter the table it measures. We imagine the universe as indifferent to our curiosity, a great machine that keeps ticking whether we watch or not. But the more physicists studied the quantum world, the more that assumption began to crumble. They discovered that when you measure a particle, the act of measurement doesn't just record what's there, it decides what's there. The heart of the mystery lies in what physicists call superposition. But let's think of it instead as a quiet shimmer of maybes. Before you look, a particle isn't in one place or another. It's in a haze of possibilities, a soft blur that includes every option the universe allows. The equations describing it, those famous wave functions, can predict the odds of each outcome perfectly. But the instant you observe, the haze disappears, leaving only one clear result. It's as if reality itself sighs and says, "Fine, if you must know, I'll be this." No one agrees on what truly happens in that moment. Some scientists treat the wave function as merely a tool, a way to keep score of what we can expect. Others see it as a real thing, a kind of invisible fabric that collapses into the tangible when we observe it. Either way, the boundary between what is and what is seen becomes impossibly thin. The experiment and the experimenter are no longer separate, they dance in a single rhythm. One famous version of this puzzle is the double-slit experiment. It's been told so many times that it feels almost like folklore, a bedtime story for physicists. Imagine you fire a beam of light, tiny particles called photons, at a barrier with two slits. If you leave the system alone, each photon behaves like a wave, rippling through both slits at once, overlapping, interfering with itself, painting a pattern of bright and dark stripes on the screen beyond. It's as if the photon has explored every path, like a wanderer who refuses to choose a road until forced. But now, place a tiny detector to check which slit the photon passes through. In that instant, the magic vanishes. The interference pattern disappears, replaced by two neat piles of dots, one behind each slit. The photon has behaved like a solid marble instead of a ripple of light. Simply by measuring, you've changed the outcome. The act of asking the question, "Which path did you take?" forces nature to pick an answer. This raises a haunting question. When does the universe decide what really happens? Does the photon know from the beginning which slit it will choose, or does it wait until someone looks? The more researchers probed this question, the stranger it became. They discovered ways to delay the decision, to let the photon pass through, hit the screen, and only afterward decide whether to measure its path. And the result suggested that the universe waits. Your later choice seems to determine whether it behaved like a wave or a particle all along. That is the quiet rebellion of quantum measurement, the idea that reality does not fully exist until it is asked to. Not in a mystical sense, but in a deeply structural one. Observation and outcome seem to arise together, like two halves of a single gesture. It's no longer possible to separate the observer from the observed. They are part of one unfolding act of creation. To make sense of this, Scientists have built entire interpretations, philosophies hidden behind equations. Some, unlike the Copenhagen view, accept that asking a question simply causes the world to choose an answer. Others, like the many worlds interpretation, claim that every possible answer happens but in different versions of reality, and we only experience one branch. A few others whisper that maybe consciousness itself, the spark of awareness, has something to do with collapse. Each attempt solves one problem and opens another. You can think of it as standing in a hall of mirrors, where every reflection seems to look back with a slightly different expression. Each one insists it's the real you, but none can be fully trusted. That's how physics feels when it tries to explain measurement. No matter which mirror you turn to, you glimpse something true, but never the whole truth. This blurring of roles, of scientist and subject, has a quiet beauty to it. It reminds us that knowledge is not a conquest, but a relationship. The universe doesn't hand out answers freely. It waits for us to ask, and even then, the act of asking changes both sides. Measuring the world is a form of participation, a moment of shared decision between mind and matter. If this sounds philosophical, that's because it is. The closer physics gets to the heart of reality, the more it begins to sound like poetry. Equations that once felt solid now describe things that flicker between being and not being, between potential and fact. The world seems less like a machine and more like a dream gently agreeing to be seen. And perhaps that's why quantum mechanics feels both terrifying and tender. It tells us that the observer is not separate from the universe, but part of its self-awareness. When you measure something, you are the universe taking a small, deliberate glance at itself. You're not outside the story. You're one of its sentences. If we follow the thread a little further, this idea grows even more unsettling. What happens when there are two observers, each performing their own measurements, each confident in their own results, and yet their realities don't agree? Can both be right? Can truth split and remain whole? The path now carries us toward a paradox that asks exactly that question. A thought experiment so haunting it has been called the moment physics began to doubt its own reflection. Picture a quiet room with a beam of sunlight slipping through a narrow curtain. Dust motes drift lazily, catching the light and swirling like tiny galaxies in a slow cosmic ballet. You lift your hand into the beam, and for a moment the light feels tangible, warm, obedient, something you can trust. Yet in the strange theatre of quantum physics, that same beam of light refuses to behave. It plays two roles at once, wave and particle, as though it can't decide what kind of being it wants to be until someone looks. The story of light's double life begins with the simplest of ideas. Fire a few particles of light, photons, toward a screen. Between the light and the screen sits a barrier with two narrow slits. What happens next has become one of the most beautiful, frustrating and important demonstrations in all of science. If you cover one slit, the photons line up neatly behind the open one, forming a simple pattern, like pebbles tossed through a doorway. But when both slits are open, the pattern changes into delicate stripes, bright and dark, like ripples on water. Those stripes show interference, something only waves can produce. It's as though each photon passed through both slits, spreading like a ripple, colliding with itself, and then painting an interference picture. Now, here's the twist. Fire the photons one at a time, carefully, slowly, giving each particle enough space to travel alone. You might expect them to form two clumps, one for each slit, but they don't. They still build that same striped interference pattern. Each photon seems to act as though it knows about the other slit, as though it has somehow explored both paths simultaneously and interfered with itself, a single particle, behaving as a wave of probabilities. But the real trouble starts when you decide to peek. If you place a tiny detector by each slit to find out which path the photon takes, the interference vanishes, the stripes dissolve. Instead, the photons line up in two simple piles again, behaving like solid little marbles. Just the act of observing which slit they pass through changes the outcome. The photons seem to sense that they're being watched. You could spend a lifetime staring at this experiment, whispering "why" under your breath, and still come away without an answer. It's not that we lack precision. The math predicts everything exactly. What we lack is understanding. What is light doing when we're not looking? Is it truly in two places at once, or does it exist only as potential until an observer forces it to decide? If we try to describe this in softer language, imagine the photon as a traveller arriving at a fork in a forest path. Instead of choosing left or right, it drifts as mist, filling both trails. Only when you step forward and ask which way it went does it solidify into one route, and the mist disappears from the other. Before you looked, every route existed. After you looked, only one remained. This behaviour isn't limited to light. Electrons, atoms, even larger molecules have shown similar strangeness. It's as if the entire universe, at its smallest scales, moves in whispers of maybes until attention falls upon it. The act of observation doesn't merely reveal the truth, it helps decide which truth is allowed to exist. Niels Bohr once said, "It's wrong to think that the task of physics is to find out how nature is. Physics concerns what we can say about nature." In other words, our experiments don't show us the universe as it is, they show us the universe as it speaks to us. That difference sounds small, but it changes everything. It means the observer is part of the grammar of reality. And still, the question lingers. What happens if the universe waits for us to ask? This led to one of the strangest twists in all of science, the delayed choice experiment. Imagine repeating the double-slit test but making your decision to observe after the photon has already hit the screen. You let the light travel freely, reach its destination, and only then, afterward, decide whether you want to know which slit it passed through. You would think that by then the story would already be written. But no, the pattern on the screen seems to depend on that later choice. If you decide to measure which slit it took, the interference disappears. If you decide not to measure, the stripes return. It's as though the photon's past behaviour, whether it went through one slit or both, was determined by your present decision. You can't use this to send messages into the past, but it feels as if the act of choosing now reshapes what was. Time itself starts to feel like another kind of fog, something that can be rearranged when you turn your gaze. Physicists describe this effect as delayed choice quantum erasure, but we can think of it more softly. The universe, in some way, waits until all the questions are asked before writing down the answers. What we call the past may be less like a carved stone and more like a soft wax tablet, rewritten as new light falls upon it. There's something almost tender in that thought. It suggests that reality is patient, that it allows for revision. The photon doesn't break the laws of time. It simply reminds us that the boundaries between past, present and future might not be as rigid as we imagine. Perhaps the universe keeps all possibilities nearby, like an artist keeping earlier drafts beneath the final painting, ready to be uncovered if needed. If you think of the photon not as a tiny object but as a note in a symphony, then measuring it is like deciding which instrument you were listening to all along. The melody changes not because the music was wrong, but because your ear chose a different harmony to follow. The song of the universe, it seems, isn't fixed. It's responsive. And so, the double life of light becomes something more than a puzzle. It becomes a mirror for us. We too exist in layers of possibility, potential choices, unrealized futures, paths not taken. Perhaps observation, in its deepest sense, is the act of awareness collapsing all that potential into the single shimmering moment we call now. This experiment, humble and haunting, was where modern physics first realized that the universe doesn't simply exist. It performs. It waits for its audience. The scientist, the student, even the quiet listener before sleep, all become part of the story being told. The curtain rises only when we look. As we drift further into the story, the next thread will take us into an even stranger version of this drama, one where two observers, each watching the same event, record two realities that cannot be reconciled, and yet both are true. It's a thought experiment so unsettling that it shakes the very definition of truth itself. Imagine you're watching a play where the actors perform first, and only after the curtain falls does the writer decide which script they were following. Somehow, when the script is chosen, the performance that already happened seems to change meaning entirely. That is what the delayed choice quantum eraser experiment reveals about the nature of light and time, a performance where the ending quietly rewrites the beginning. To see how it unfolds, picture a single photon leaving a source and facing two possible paths, like a traveller at crossroads. Each road is marked by mirrors and tiny detectors that can either record which path was taken or erase that information. If no one keeps track, the photon behaves as a wave and creates an elegant pattern of interference, its presence spread out like a sigh across both paths at once. But when a detector notes the path, the wave collapses into a simple dot, one decision, one location. It's as though curiosity itself forces the photon to commit to a single story. Here is where things become almost mythic. In the delayed choice version, you allow the photon to complete its journey, to hit the screen and leave its mark before you decide whether to keep or erase the record of which path it took. Only after the fact do you separate the results. The group where the path information was kept shows no interference, while the group where the information was erased displays the familiar wave pattern. It's as if the photon knew what kind of question you would ask long after it finished answering. Of course, no one believes information actually travels backward in time. The screen does not magically rearrange itself. The interference only appears when all the data are grouped later and viewed together. Still, something about this arrangement unsettles our sense of sequence. We're used to thinking that causes come first and effects follow. Yet here, the decision you make in the present determines which version of the past becomes visible. Perhaps the simplest way to imagine it is to think of the universe as a book written in invisible ink. The words appear only when you choose how to read them. Each choice of question, each act of measurement, illuminates one version of the story while erasing the others. The past isn't erased in a violent way. It's rewritten in whispers, rearranged quietly under the surface. Some physicists explain the effect by saying the photon never had a definite history at all until we organised our observations. Others describe it through something called quantum entanglement, the idea that particles remain linked, sharing information even across distance. In the eraser experiment, the photon's path is entangled with another photon, acting as a kind of messenger. What we choose to do with the messenger, whether to read its message or discard it, determines how the first photon's behaviour looks to us. No signal moves faster than light. The universe merely coordinates its story so that everything remains consistent. But that explanation, however logical, does little to soothe the feeling that time itself has loosened. The equations describing light work both forward and backward, symmetrical in time, like a melody that can be played in reverse without sounding broken. Perhaps the experiment simply exposes that symmetry in a way our minds are not built to accept. To us, the flow of moments feels sacred. We wake, act, sleep, and never in reverse. Yet at the smaller scales, nature might see no difference between yesterday and tomorrow. If we soften the math into imagery, we can think of time not as a river running from source to sea, but as an entire lake held still in one vast reflection. Each moment is a ripple, and when we observe one, the pattern of every other ripple adjusts to stay in harmony. In this sense, the future doesn't rewrite the past, it completes it. The whole lake must shimmer in one coherent design. There's also something poetic about how this paradox echoes the way memory works in our own minds. A memory changes slightly each time we recall it. We believe we are retrieving the past, but in truth, we are rebuilding it. The act of remembering is a kind of measurement, and the story we tell about who we were depends on who we are now. In the same way, the photon's past seems to adjust to the observer's present choice, as if the universe too keeps editing its memories. If we follow the thread even more gently, another possibility appears, that maybe the universe does not operate on linear cause and effect at all. Perhaps every event is part of a network of relationships, each influencing the other across time as well as space. In that picture, the photon's behaviour doesn't violate causality. It simply obeys a rule more subtle than our everyday logic. The future and the past, instead of being 2 points separated by an arrow, become partners in a quiet dance, shaping each other in balance. The delayed choice experiment reminds us how deeply our sense of time is tied to our sense of self. We like to think that the past is fixed because it anchors us. If even light can have its history rewritten, what does that say about us? About the moments we thought were finished? Perhaps every instant is still alive somewhere, still waiting for the right kind of attention to reveal a different pattern. The beauty of these findings is that they don't demand fear, only humility. The photon is not mischievous, and time is not broken. What these experiments show is that our human concepts, before and after, cause and effect, are not the universe's native language. They are translations made for comfort, and sometimes translations lose nuance. If you close your eyes for a moment and imagine all of time as one great painting, you might picture yourself as a brushstroke upon it. Each movement of your attention adds colour to a part of the canvas that was once faint. The picture isn't static, it breathes with observation. What we call the present may simply be the act of the universe noticing itself. From here, the story opens into an even more puzzling question. If a single observer can influence how the past looks, what happens when two observers look at the same event and disagree about what happened? Can both be right? Can the universe hold two incompatible truths at once? The trail of clues now leads us toward a thought experiment that challenges not just time, but reality itself. The one that asks whether two scientists can live in different versions of the same moment and never know. Imagine a quiet laboratory, sealed behind heavy glass. Inside, a scientist leans over a small device that measures the spin of a single particle, a tiny quantum coin that can land either up or down. The room is hushed, lit only by the pale hum of a monitor. The scientist presses a button, the detector clicks, and a result appears. Spin up. To the scientist inside, the world has spoken clearly. The measurement is done, reality has chosen its side. Now step outside that room. Another scientist waits in the hallway. This one is Wigner, the friend's friend, the observer of the observer. Wigner hasn't looked yet. To him, the laboratory is still part of a larger quantum system. Inside that sealed room, the particle, the measuring device, and even the scientist are all tangled in a blur of possibilities. The friend may have seen spin up, or spin down, or some strange mix of both that hasn't yet been resolved. From Wigner's perspective, until he opens the door and checks, the entire lab exists in superposition. A word we can think of softly as a cloud of maybes. So here we are. One event, two witnesses, and two versions of truth. Inside, the friend is certain the result is fixed. Outside, Wigner believes the result is still undecided. Both are correct in their own frame of reference. The question that keeps physicists awake is this: which version is real? For a long time, Wigner's friend was only a thought experiment, a story meant to show how deeply strange the act of measurement can be. It was a cousin to Schrödinger's cat, but with an added twist. The cat could tell you what it saw. Yet in 2019, a team of physicists in Vienna performed a simplified, real-world version of the idea. Using pairs of entangled photons, they recreated the logic of Wigner's paradox and found results that echoed his nightmare. two observers could record conflicting realities, and both results fit perfectly within the predictions of quantum theory. That's when the experiment stopped being just philosophy. It became something real, measurable, and deeply unsettling. It showed that, under certain conditions, there may be no single, objective sequence of events that everyone must agree on. The world could be a patchwork of perspectives, each internally consistent, each complete on its own terms, yet impossible to merge into one unified truth. To make sense of this, it helps to step back and think about what a fact really means. In everyday life, facts are things everyone can agree on. The sun rose this morning, water freezes at 0 degrees. But in the quantum world, a fact may not exist until someone observes it, and even then, it might belong only to that observer's version of reality. It's as though each measurement writes a private entry in the universe's diary, and no two entries can be compared without changing both stories. You might imagine it like two people watching a coin tossed through different windows. One sees it land heads, the other tails. Neither is wrong. They're simply watching different aspects of the same event, each from their own isolated frame. In classical life, that couldn't happen. The coin can't land both ways. But in quantum mechanics, it can, because before anyone compares notes, the outcome is still entangled with the act of observation. Reality doesn't seem to decide until the observers share their experiences, and by then, something new is written. There's something hauntingly human about this. It echoes the way we live our own lives, each person inside their own small laboratory of perception, recording the world as it appears to them. Your reality, my reality, the scientist's reality, each feels complete and solid from the inside, yet none can fully contain the others. When we meet and exchange what we've seen, we try to merge our stories into one picture, but something always gets lost in translation. The universe, it seems, operates the same way. Some interpretations of quantum mechanics, such as the many worlds view, imagine that both outcomes are real, but in separate branches of existence. In one version of the universe, the friend observes spin up. In another, spin down. Wigner opens the door into only one of these realities, while countless others continue quietly beyond reach. Each observer moves along their own thread in a vast cosmic tapestry, where every possible outcome finds its home. Other physicists take a softer stance. They suggest that reality isn't split into worlds, but woven from information. In this view, a measurement doesn't collapse a wave, it updates the knowledge of the observer. Wigner and his friend hold different knowledge, and only when they compare notes does the shared picture become complete. Even then, that completion might erase the individuality of their experiences. If this sounds philosophical, that's because it is. Quantum physics has a way of slipping between science and philosophy like water between stones. At its core lies a simple, quiet question. Does the universe exist independently of us, or is it partly shaped by the act of being known? Wigner's friend doesn't answer that question. It just makes it impossible to ignore. When you think about it, this paradox carries a certain beauty. It suggests that the universe might not be a single stage where everyone watches the same play, but a theatre of many spotlights, each illuminating its own corner. The show looks different depending on where you sit, and maybe truth itself is not a single, unchanging thing, but something relational, unfolding through interaction. It also hints at something quietly hopeful, that observation, awareness, and perspective are not intrusions into reality. They are part of its fabric. Every observer, whether a scientist or a single photon, adds a brushstroke to the cosmic canvas. The act of looking isn't just seeing, it's participating. If you close your eyes and imagine that sealed lab again, you might sense how fragile and beautiful this idea really is. Two people, two truths, both valid. Each sees a piece of the world that cannot be taken away from them. Reality, it seems, isn't a single photograph. It's an album of overlapping exposures layered so tightly that together they form the illusion of solidity. And if that's the case, then what we call truth might be something local, something that lives only within each perspective, fragile and fleeting like a reflection on glass. Our quiet exploration now turns to this idea. What if truth itself depends on the way we ask the question? What if, by the time the answer appears, the question has already changed it? Picture a darkened room with a single beam of light streaming through a crack in the ceiling. You walk slowly across the floor, and as you move, the beam shifts. Shadows change shape. Dust dances differently. Nothing in the room has changed, and yet everything has. In the quantum world, the truth behaves much the same way. The answer you find depends on how, when, and even that you ask. The question reshapes the answer while it's being spoken. This idea is known, in the language of physics, as contextuality, but we can think of it more gently as the art of timing between question and answer. In the everyday world, it doesn't matter how you look at something. The coffee cup on your desk is still a cup whether you tilt your head left or right, but deep inside the quantum realm the situation changes. There, the properties of things, their spin, their position, their energy, do not exist in isolation. They seem to depend on the whole context of the experiment, which measurements are made, what order they come in, even what other questions are being asked nearby. Imagine walking into a room full of mirrors and asking, "What colour am I wearing?" Each mirror reflects you differently, warm in one, pale in another, green tinted in the next. You're still the same person, but each reflection offers a slightly altered truth, shaped by the frame that contains it. That's how nature behaves at the quantum level. The property you try to observe is not fixed, it's woven into the conditions of observation. To test this, physicists perform experiments that play with these boundaries. They create setups where particles must respond to questions asked in varying orders, and somehow the answers refuse to fit together into one consistent story. The results obey the mathematics perfectly, but resist the kind of logic we expect from the macroscopic world. It's as if the universe keeps multiple storylines alive, allowing each question to write its own version of reality without collapsing the others completely. This defiance of single truth extends further when we reach something called non-locality, a word that sounds heavy but can be softened into an image. Think of it as the universe's way of whispering across distances. Einstein once called it spooky action at a distance, though the spookiness has softened with time. It simply means that particles once connected can still respond to each other instantly, even when separated by vast space. They're like two notes, from the same chord, still resonating together after the instrument is gone. Bell's theorem, often described with formidable equations, proved something startling and strangely tender. It told us that if the universe were truly local, if each particle only cared about its immediate surroundings, then certain patterns in their correlations would never appear. But they do appear every time. This means that nature either allows subtle influences to travel faster than light, or more profoundly, that distance itself might not be as real as we think. To make that less abstract, imagine two friends who grew up learning the same melody. They move to opposite ends of the earth, lose contact for years, and then, on the same quiet night, both hum that tune without knowing why. No message passed between them, yet their notes align. In a way, that's how entangled particles behave. They share a rhythm that space can't silence. When we listen to this rhythm, we begin to realize that truth in the quantum sense may not be a single, global law, but something that exists in small pockets, local truths born of local perspectives. Each observer, each measurement, creates its own moment of agreement with the universe, and when we try to merge these perspectives, they don't always line up. The contradictions don't mean something's broken. They simply remind us that reality may be more like a symphony heard from many balconies, each echoing slightly differently across the hall. For a moment, imagine the cosmos not as a grand stage lit from above, but as a field of scattered spotlights. Each observer's light shines on a portion of the performance, illuminating one angle, one gesture, one detail of the dance. From your vantage point, the story seems clear. From another, it looks entirely different. But both views are part of the same larger choreography. If all lights could be combined, perhaps the full performance would appear. But the paradox is that combining them changes the show itself. The audience and the actors are inseparable. There's an elegance to this that mirrors human experience. Every day we live inside our own contextual realities. The same conversation, remembered by two people, carries two different truths. A smile might mean warmth to one, pity to another. Memory itself behaves like a quantum property, shifting subtly each time we recall it, recoloured by the context of the present. Perhaps this is not coincidence but reflection. The macro world mirroring the micro, each whispering that truth is never isolated from perspective. As we drift deeper into these ideas, it becomes tempting to think of knowledge not as something we collect, but something we co-create. The universe doesn't reveal itself passively. It engages with us. It answers the way a poet does, not with absolute statements, but with responses shaped by the mood of the question. In this sense, the cosmos may be less a library of facts and more a conversation unfolding in infinite dialects of observation. What begins as a scientific insight unfolds quietly into philosophy. If reality depends on how we look, then there may never be one ultimate picture, only overlapping impressions, each true in its own light. Certainty, it seems, belongs to no one. Instead, what remains constant is relationship, the delicate interplay between observer and observed, question and answer, cause and effect. Perhaps that's why quantum physics, for all its paradoxes, feels oddly peaceful when spoken softly. It tells us that the universe is participatory, alive, listening, that it allows multiple truths to coexist without demanding a single winner. And that, in itself, is a kind of harmony, an orchestra of perspectives, none more real than the other, each completing the music in its own way. From here, the path carries us toward a larger, slower question, one that hums beneath all others. If truth can depend on where and when we stand, what about time itself? Could the flow we call before and after be another form of context, another illusion shaped by how we watch? Our next quiet step takes us into that territory, where time stops obeying direction and begins to fold in both ways, like the tide breathing in and out. Every morning begins with motion. The kettle warms, the steam rises, and light slowly climbs across the walls. You watch the water boil, and never once do you see it flow back into the tap. To us, this feels so obvious that we forget it's an assumption, that time always moves forward. Day follows night, cause leads to effect. Footprints point one way down the beach. Yet in the deepest laws of physics, this simple rhythm doesn't exist. The universe, at its most fundamental level, doesn't know which way time should go. The equations that describe motion, energy, and light work perfectly whether you run them forward or backward. It's only our lives that insist on direction. Imagine a film of waves crashing on the shore. Played backward, the water still looks like water. The physics works in both directions, yet our minds flinch, because life doesn't unfold that way. The arrow of time feels sacred, written into our experience. We age, we remember, we move from what was toward what will be. Entropy, the gradual spread of disorder, gives this flow its familiar pull. A broken cup doesn't reassemble, smoke doesn't crawl back into the match, but that's a property of large, warm things, collections of countless particles. On the smallest scales, in the silent space of quantum events, time can shimmer in both directions without contradiction. In those realms, a process and its mirror image are almost indistinguishable. A photon can travel from one point to another and the mathematics describing that journey would look the same if you reversed it. The universe doesn't mind whether a particle moves from past to future or future to past. It only cares that the relationships among all moments stay consistent. It's like a dance where each step can be retraced perfectly, leaving no footprints to mark the preferred direction. That realization unsettles the human sense of order. We like beginnings and endings, causes and consequences. But the quantum world is a strange storyteller. It writes the middle of the tale first, then lets the ends emerge later. When scientists examine the behavior of particles through their equations, they often find that time is not so much a river as a lake, still, complete, reflecting every event at once. What we perceive as flow may be nothing more than the way our consciousness drifts across that reflection, tracing one path among countless possible ripples. Some physicists call this time symmetry, a phrase that sounds austere but hides quiet poetry. It means that for every way the universe can evolve forward, there exists a perfectly valid mirror evolution backward. If we could look closely enough, we might see both stories overlapping, like two transparent films projected on the same wall. Our perception of direction arises only because we're part of one of those films, carried along by entropy, memory, and the tiniest symmetries that define living experience. Think of how memory works. You can remember yesterday but not tomorrow. The arrow of time to you is simply the arrow of remembering. Yet the particles that make up your brain don't care which way they spin through time. They only respond to the laws that guide them, and those laws make no distinction between the act of remembering and the act of anticipation. Perhaps what we call the future is just a region of the universe we haven't yet learned to recall. To picture this more softly, imagine a snowflake drifting through still air. It twirls, melts, and vanishes. Reverse the film, and the water droplet reforms, floats upward, freezes back into crystalline perfection. Both motions obey the same physical rules. What changes is our sense of meaning, the emotional texture that says one version is natural and the other absurd. But to the equations of quantum mechanics, the two are equally valid stories. There is a quiet comfort in realizing that the universe itself isn't bound by our one-way sense of time. It suggests that loss and decay, though real to us, are not absolute. Every moment still exists somewhere in that vast timeless landscape. The laughter you once heard, the hand you once held, the sunlight on an old afternoon. The past doesn't vanish, it simply drifts out of the region your awareness can reach. Some philosophers imagine this view as a block universe, all of space-time laid out like a completed sculpture. We walk along it slice by slice, experiencing one thin layer of its structure and calling that the present. The future is already there, waiting patiently for us to arrive. The past remains behind, unchanged. From this perspective, time doesn't flow at all. It is we, who move, carried gently along the corridors of a fixed yet living geometry. And yet, for all its symmetry, this picture doesn't make our experience less meaningful. If anything, it deepens it. The moment you breathe now, this heartbeat, this quiet listening, exists eternally within that sculpture. It never truly ends. The arrow of time that carries you forward is not a force but an illusion, a consequence of how memory, entropy, and consciousness intertwine. You could think of it as reading a novel. The story is already written from beginning to end, but you experience it line by line. To the book, every page is equally real. To you, the story feels alive because you're inside it, discovering what happens next. The universe might be the same, complete, still, yet always unfolding when seen from within. As our understanding of quantum mechanics grows, these ideas of time without direction become less like poetry and more like glimpses of a hidden truth. Even Einstein's relativity hints at it. The speed of light marks a boundary beyond which time and space trade rolls. The laws themselves don't prefer forward or backward, only consistency. It's we who have preferences, shaped by the thermodynamic flow of warmth and decay that defines life. So if the universe doesn't know the difference between yesterday and tomorrow, why do we? Perhaps it's because we're made of patterns that remember. Our bodies, our thoughts, our world all depend on processes that increase entropy, turning order into diffusion, structure into story. Time, to us, is memory's shadow, the trace of what can't be undone. But beyond that shadow, the cosmos may be as timeless as a single breath held forever. As we linger on this thought, the distinction between cause and effect begins to soften. We start to wonder whether the future could influence the past as easily as the past shapes the future. Could what we call destiny be just another kind of reflection, light bouncing backward across the still surface of time? If we follow the thread a little further, we enter a world where events seem to meet in the middle, where away from the future and away from the past converge to create the moment we call now. If you close your eyes for a moment and imagine time as a great sea, you might picture waves rolling endlessly toward the shore. But beneath the surface, another motion exists, a quiet undercurrent that drifts in the opposite direction, pulling backward, balancing the flow. The ocean does not choose forward or backward. It moves both ways at once, shaping itself through this hidden symmetry. Some physicists believe the universe may be the same, its fabric woven not from a single arrow of time, but from two threads, one stretching from the past and one from the future, meeting gently in the present. This strange and beautiful idea is known as retrocausality, though it need not sound technical at all. It simply asks, what if the universe's story is written from both ends? What if the present moment is a collaboration between yesterday and tomorrow, a meeting point where two kinds of influence softly intertwine? In the world we know, cause and effect feel sacred. You drop a pebble, and only then do the ripples spread. You speak, and only then do the echoes return. But quantum physics keeps hinting that this familiar sequence might not be the whole picture. The delayed choice experiments we explored earlier already showed us how a decision made in the present can seem to reshape what happened before. Retrocausality takes that idea seriously, not as a paradox, but as a deeper kind of balance. In this view, every event is determined not only by its past, but also by the constraints of its future. A particle doesn't simply follow a path laid out behind it. It also aims for a destination ahead, adjusting its journey so that the beginning and end harmonize. Like a melody that sounds complete only when both first and last notes are heard, the universe composes each moment with both directions in mind. To understand how this might work, we can borrow a gentle image from a theory called the two-state vector formalism. Imagine two waves flowing through the same sea. One moves forward in time from the past, the other moves backward from the future. Where they meet, their ripples combine to create the moment we experience as now. This doesn't mean messages travel from the future to change the past. It simply means that both boundaries matter. The universe is not a sentence being written left to right, but a poem whose first and last lines shape the rhythm of all that lies between. In the language of physics, this picture remains perfectly lawful. The equations describing motion are symmetrical in time. They make sense whether you read them forward or backward. What changes is our role within them. We experience the forward-flowing half because that's how memory and entropy carve their path through us. But to the universe itself, there is no preferred direction, only the eternal consistency of all its moments, fitting together like a grand mosaic. You can think of retrocausality as the universe's way of keeping its story coherent. Imagine you're solving a maze. You could begin at the entrance and try every path until you find the way out, or you could start from the end and trace backward to meet your earlier steps. Either way, you'll find the same route, but working from both directions at once might make the journey smoother. The cosmos perhaps does something similar. It doesn't rewrite history, it coordinates it, ensuring that beginnings and endings always match. There's a quiet beauty in this vision, because it softens the harsh edges of fate and chance. It suggests that what we call free will and what we call destiny might not be enemies at all. The future could be less a rigid script and more a partner in dialogue with the past. When you make a choice, you're not simply reacting to what came before, you're helping the universe settle on the version of itself that fits both ends of its timeline. Every decision becomes a meeting place where possibility becomes pattern. Think of how a painter works. She may begin with rough strokes and vague ideas, but as the painting nears completion, the first brush marks gain new meaning. The earlier colours start to look inevitable, guided by what they became. Our lives may function in a similar way. The moments we live now may give shape to the memories that seemed fixed long ago. The past feels solid, but perhaps it too is waiting for the rest of the painting to dry. Einstein once said that for those who understand physics deeply, the distinction between past, present and future is only an illusion, albeit a stubborn one. That illusion, though, is a comforting one. It allows us to feel the warmth of progression, the promise of change. Yet even within that flow, retrocausality whispers a gentler truth, that every moment, even the fleeting one you're living right now, is already woven into the full tapestry of time. You're not falling through moments, you're suspended within them, part of the pattern that stretches both ways. If we allow this thought to settle softly, it becomes something almost spiritual. The future is not waiting ahead of you like a blank page. It is already here, quietly reaching back, shaping your path with invisible hands. And the past is not gone. It lingers behind, adapting itself to the story that's still unfolding. Each breath, each thought, each act of kindness you offer may ripple not only forward into what will be, but backward into what was, completing the symmetry of a universe that values coherence more than sequence. When we let go of the need for time to flow like a river, we begin to see it as a sculpture, complete, unchanging, yet experienced one surface at a time. The sculpture itself doesn't move. The observer does, sliding across its contours of cause and effect, seeing a new face of eternity with each step. Every moment is eternal in its own right, each a meeting of two infinite directions, the arrow of memory and the arrow of possibility. It might seem abstract, but in this vision, physics and poetry finally meet. The mathematics that frighten most of us, symbols of symmetry, of boundary conditions, are simply the grammar of balance. They tell us that the universe is not a chain of dominoes, but a web of mutual influence. Nothing is ever purely cause or purely consequence. Everything participates in everything else. As we drift further into this reflection, a new question begins to take shape, gentle yet electric. If time can move both ways, what about connection itself? Can two things remain linked across distance, speaking in silence, like mirrored tides across the same ocean of time? The trail of clues now leads us toward that very mystery, the story of how particles whisper to one another without ever sending a message, and why their quiet harmony might hold the secret to unity itself. Imagine two candles lit in separate rooms. You extinguish one, and for a fleeting instant the other flickers, as if it felt the loss. That isn't how candles behave in the ordinary world, of course, but in the strange calm of quantum reality, something like that does happen. Particles that were once close can remain mysteriously connected, no matter how far apart they drift. A change in one can instantaneously echo in the other, as though distance were nothing but an illusion of perspective. This quiet entanglement began as a puzzle, born in the mind of Albert Einstein nearly a century ago. He called it spooky action at a distance, and you can almost hear the discomfort in his voice. The idea that information could leap across space faster than light seemed to break everything he held sacred about the universe. But quantum physics didn't mind his discomfort. It continued to behave as though the universe itself were whispering between its pieces, maintaining connections invisible to any messenger. To imagine it softly, Think of two bells forged from the same metal. You place them on opposite sides of the planet, strike one, and though the other remains silent, it vibrates faintly with the same tone. Not because sound crossed the oceans, but because they share something deeper, the same origin, the same harmony. Entangled particles are like that. When they're created together, they become parts of a single quantum state. One melody played on two instruments. Whatever happens to one must be balanced by what happens to the other, even if they are light years apart. This isn't telepathy or secret communication. No signal travels between them. It's more precise to say there is no distance to travel across in the first place. Entangled particles are not two things. They're one system, stretched out across space like a single shimmering thread. When you measure one end, you're not sending information to the other. You're revealing what was always true for both. Space only makes it look like a conversation when it's really a shared silence. The first experiments to test this connection were almost theatrical in their simplicity. Physicists sent pairs of photons in opposite directions and measured their polarizations, the way their electric fields twist through space. The results refused to obey the local logic Einstein trusted. Time and again, the photons' behaviors correlated in ways that defied explanation by hidden mechanisms. It wasn't that they were secretly signaling each other. They were simply continuing a dance that began before they parted. John Bell, a gentle mathematician from Northern Ireland, found a way to put this mystery into numbers. His theorem showed that no local, classical model, no theory that keeps causes and effects confined to their neighbourhoods, could reproduce the strange correlations quantum mechanics predicted. The universe, in Bell's quiet handwriting, turned out to be non-local, meaning its parts can behave as though they are immediately aware of one another. The formulas, though simple to him, spoke a truth that still ripples through physics today. Nature doesn't care for our boundaries. If those equations sound distant, we can translate them into something closer to feeling. The world, at its smallest scales, behaves less like a collection of objects and more like an unbroken field of relationships. Every particle, every spark of light, every atom of your body is woven into this field, resonating faintly with everything else that ever was. The connections fade with distance, but they never vanish entirely. You are, quite literally, entangled with the universe. There's a certain tenderness in that thought. It means that nothing is ever entirely alone. Every interaction leaves a trace, every touch, a lasting echo. When you hold someone's hand, when two atoms in your body collide, tiny fragments of their quantum states mingle. They drift apart again, yes, but the pattern of that meeting remains written into the shared wave that describes you both. Over time, through countless exchanges, every bit of matter in the cosmos becomes faintly aware of every other. Entanglement challenges our intuition, but it also comforts something deeper in us, the yearning for unity. It whispers that separateness might be a useful illusion, not an ultimate truth. The world is stitched together not by visible threads, but by coherence, by symmetry, by the quiet insistence that everything once joined remains part of one continuous whole. If you look up at the night sky and imagine two stars born from the same cloud of gas, billions of kilometers apart, shining their light in opposite directions, it's easy to think they've forgotten each other. Yet, in a quantum sense, they're still participants in the same cosmic dance, their energies linked by the laws that first gave them life. The universe is vast, but connection travels not through distance, only through relation. This phenomenon is more than philosophical curiosity. It's the foundation of modern quantum technologies, encryption, teleportation, computing. In laboratories across the world, scientists harness entanglement to send information in ways classical physics forbids. Yet even amid this precision, the mystery remains. No experiment has revealed a hidden mechanism behind the link. It is as if reality itself insists on remaining a single story told in two voices. There's a poetic symmetry here too. Earlier we wondered if time could flow both ways. past influencing future, future guiding past. Entanglement adds another layer. Perhaps space too is not as rigid as we imagine. Time, distance, individuality, all soften into gradients of relation. The universe may not be a vast stage where separate actors perform, but one immense performance in which everything plays every role. You could think of it like a great choir. Each voice sings its own part, but the harmony exists only because all voices are intertwined. Take one away, and the song loses meaning. When physicists talk about non-local correlations, what they're really describing is the universe's commitment to coherence, its refusal to let the music fall apart. If you ever feel small beneath the stars, you might remember this. You're not outside the symphony. Every atom that composes you once shared its rhythm with others, in stars, in oceans, in forgotten comets. You're a continuation of patterns older than time as you know it, patterns that still hum quietly in the fabric of existence. And if everything can remain connected across vast distances, perhaps it's not only particles that do so. Perhaps memory, empathy, even thought are echoes of this same unity, the macroscopic shadows of a deeper entanglement. Physics cannot yet say, but poetry has known it for centuries, that what touches one thing may, in ways unseen, touch all. As we follow this harmony further, a new puzzle awaits, one that takes this connection to its most impossible extreme. What if two minds could solve a problem perfectly without ever communicating, as though they were sharing a single thought? What if entanglement could look, to us, like telepathy? The path now carries us toward that quiet and beautiful contradiction, where coordination arises out of silence and logic bends gracefully to the rhythm of mystery. Imagine two people playing a game. They sit in separate rooms, unable to see or speak to each other. Each is asked a series of questions, and they must respond with only yes or no. The rules are simple, but the twist is impossible. Their answers must always match in a particular pattern, one that no pair of isolated players could coordinate without cheating. Yet somehow, if they share an entangled connection, if their very particles are linked, those impossible matches appear again and again, as though the two minds were quietly sharing a single thought across the walls. This isn't science fiction. It's a simplified version of a family of experiments sometimes nicknamed quantum pseudo-telepathy. The name sounds strange, but what it really means is that entangled particles can win coordination games that classical physics says they should always lose. The results defy our intuition, but follow the same quiet rules we've been exploring. Connection without communication, harmony without exchange. To imagine it gently, picture two dancers standing on opposite sides of a curtain. They can't see each other, can't signal or count aloud. Yet each step they take matches perfectly with the other's rhythm. When one raises a hand, the other turns their head, every movement aligned. It isn't that they're guessing, it's that both are following a shared choreography, written into the very floor beneath their feet. The universe, it seems, can hold patterns that extend across separation, allowing distant parts to move as one. In the human story, we often long for such silent understanding. We dream of people who can finish our sentences, sense our feelings from far away, feel what we feel. Entanglement is not that kind of empathy. It doesn't carry words or thoughts, but it suggests that the physical world itself may be built on a similar kind of intimacy. What we call space might simply be the soft distance between partners in the same cosmic dance. In physics, this phenomenon has been tested through versions of what's called the Bell game, or sometimes the GZ scenario, names that can sound cold, but their meaning is gentle. They show that two or more particles, once entangled, can display a level of coordination that no local rule can explain. There's no messenger racing between them, no signal darting faster than light. And yet their outcomes line up with uncanny precision. as if the answers were decided not in one place or the other, but in the relationship itself. The simplest way to think of it is like a pair of dice that always roll complementary numbers. When one shows a 3, the other shows a 4 every time, no matter how far apart they're thrown. You might suspect hidden strings or secret agreements, but every attempt to find such tricks has failed. What's left is a quieter understanding that the two dice are not truly separate. They are one event seen from two angles. The magic of this realization is that it dissolves the need for anything supernatural. The universe doesn't cheat, it simply refuses to divide itself cleanly. What we thought were individual pieces are fragments of a single whole, entangled in ways we're only beginning to glimpse. The apparent telepathy is just the visible surface of an underlying unity. You could also think of this as a vast mural painted on both sides of a wall. From where you stand, you see only one side. Shapes, colours, incomplete patterns. Someone on the other side sees different shapes, different colours, yet together the two images form one perfect design. The wall hides the connection, but the symmetry remains. Each brushstroke is aware of its twin, though neither side ever needs to peek. In the laboratory, such coordination is no mere curiosity. It has become the foundation of quantum communication, the dream of transmitting information not by pushing it through space, but by shaping relationships that already exist. Quantum cryptography, teleportation, and computing all grow from this principle. Still, scientists tread carefully. No message or thought can leap across entanglement faster than light. What it offers instead is assurance, proof that 2 points share the same secret rhythm, no matter the miles between them. There's a kind of gentle metaphor hiding in all this. It tells us that coherence, the ability to remain connected through uncertainty, is one of nature's favourite languages. Even in human life, the most profound bonds often rely not on communication, but on resonance. Two people, thousands of kilometres apart, looking at the same moon and feeling something similar without saying a word. Quantum pseudo-telepathy shows that the universe itself might be built on that kind of resonance. And maybe that's the deeper message of these experiments. They aren't really about particles performing tricks. They're about the way the universe balances information, ensuring that meaning stays consistent even when voices can't be heard. Each particle acts locally, following its own script, but together they compose a story that only makes sense in the whole. In a strange way, it's like reading 2 pages from opposite sides of a book. Each makes sense alone, but the true story lies in the connection between them. If we let our thoughts drift a little further, there's a quiet philosophy hidden in this harmony. What if everything that exists, stars, cells, people, thoughts, is not truly separate, but an expression of shared context? What if we misunderstand the universe by thinking of it as made of things, when it might be made of relationships? Quantum entanglement is not just a scientific result, it's a gentle hint that perhaps existence itself is relational. And yet, despite the wonder, there's humility here too. Entanglement does not let us control the world with our minds, or send secret messages to the past. It simply reminds us that control and separation are illusions of scale. The universe does not need to transmit signals when it was never divided to begin with. The cosmic choreography has already been written. Our measurements are simply the steps through which we rediscover the rhythm. If you sit quietly for a moment and think of all the moments in your life that felt coincidental, someone calling just as you thought of them, 2 ideas arriving from distant places in perfect harmony, you might glimpse the same feeling that the physicists felt, the world aligning for a breath of time, as though everything were quietly in tune. Quantum physics doesn't claim to explain such coincidences, but it does whisper something comforting behind them. That beneath the apparent chaos, everything shares one origin. The illusion of quantum telepathy isn't about reading minds. It's about realizing that there might be only one mind large enough to hold it all. The mind of the universe, thinking in patterns too vast and too quiet for us to notice. And each of us, Every atom, every heartbeat is a note in that single thought. From here, our quiet exploration drifts toward one of the most haunting scenes in quantum reality. A story where something seems to leave its own body behind, where a property detaches from the object it belongs to, like a grin floating in the air after the cat has vanished. The path now carries us toward that peculiar and poetic mystery, the quantum Cheshire Cat, and the lesson it leaves about what it means to exist at all. Imagine walking through a quiet hallway lit only by moonlight. At the far end, you catch a glimpse of a cat. Its eyes glimmer, its whiskers tremble, and then, in the blink of an eye, its body vanishes. For a heartbeat, only its grin remains, floating gently in the air before fading too. You might think this is a dream, or perhaps a trick of the light. But something eerily similar happens in the quantum world. An experiment where a particle seems to lose its own property, like a smile lingering long after the face is gone. The story begins with a simple question that scientists have asked for decades. Can an object be separated from its characteristics? Can a thing exist apart from the traits that define it? At first, the idea sounds absurd. How could you remove spin from an electron or colour from a photon? Yet in 2014, a team of physicists in Israel performed an experiment inspired by the grin of Lewis Carroll's Cheshire Cat, and their results seem to suggest that, at least in the quantum sense, such a thing might be possible. In their experiment, a beam of neutrons was sent through a carefully designed maze of paths, mirrors, and detectors. Neutrons, like tiny spinning tops, have a property called spin, an orientation that can be thought of as up or down. In the experiment, the neutrons were placed into a delicate quantum superposition, meaning each neutron took two paths at once, softly overlapping like two versions of the same traveller exploring different routes. At the end of the maze, the detectors were set to measure where the neutrons went and how their spins behaved, and the result, when pieced together, painted an astonishing picture. The neutrons' bodies appeared to travel one path, while their spins behaved as if they were taking another. It was as though the grin had slipped off the cat and gone wandering on its own adventure. Of course, no one truly believes the spin floated away like a ghost. What's really happening is subtler, a delicate play of probability and measurement, revealed through something called weak measurement. In ordinary experiments, observing a particle's property forces it to choose, collapsing its quantum haze into one outcome. But a weak measurement is more like a whisper than a shout. It peeks at the system without disturbing it too much, gathering hints rather than certainties. The result is a faint trace, a suggestion of where the particle's different aspects might be hiding before they settle into one visible form. We can imagine it like walking across a snowfield in twilight. If you stomp, your footprints are clear and deep, but the act changes the snow itself. If you tiptoe, you leave barely a mark, only faint impressions that, when traced together, reveal where you might have gone. In the Cheshire Cat experiment, the weak measurements were those faint impressions showing a pattern where the particle's mass and its property seem to take separate paths before reuniting. To describe this without the mathematics is to speak in metaphor. The wave function, the soft cloud of probabilities that represents a quantum object, is not a solid shape. It's a field of potential, capable of weaving traits through space like threads in a tapestry. Sometimes, under the right conditions, those threads can be teased apart, revealing that what we call an object is really a bundle of relationships. The particle and its spin are not two distinct things. They are two patterns within one larger wave, two ripples that can briefly drift apart and still remain part of the same sea. There's something strangely comforting in that image. It suggests that identity, whether of a particle, a person, or a planet, is not something rigid. It's a network of properties temporarily holding together, whispering to one another through the field that connects them. When the field shifts, the pattern shifts. The grin moves away from the cat, but both remain parts of the same invisible whole. If you listen to this story as a bedtime tale rather than a scientific paper, it becomes a parable about perception. What we call objects might be illusions of stability, born from how we interact with the world. A tree is not just wood and leaves, it's the play of sunlight, air, and gravity weaving together a momentary form. In that sense, the Cheshire Cat experiment doesn't just describe quantum particles, it describes everything. Every person, everything, is a temporary alignment of properties that may one day drift apart, leaving behind faint traces of the patterns we once were. Some physicists argue that the effect is not proof of separation at all, but simply an artifact of how we choose to measure, and that's true too. But even if the grin never truly leaves the cat, the lesson remains. The boundaries we draw between things and their properties may not be fundamental. They're conveniences of language and perception. The universe underneath might not recognize such separations at all. Think of how you remember someone you love. You might recall their laughter, their warmth, their voice. But those are not the person. They're echoes of relationships, qualities that exist only in the space between memory and presence. Yet together, they form a picture that feels whole. The quantum world might work the same way. Wholeness, identity, and separation could be illusions that depend on how gently or firmly we choose to look. In this view, the universe is less like a collection of objects and more like a melody. Each note, each particle, has meaning only in its relation to others. To listen to the melody is to hear how all those relationships intertwine. When we isolate one note, we lose the song. When we let the music breathe, we hear harmony instead of fragments. Perhaps that's why experiments like this feel almost spiritual in their implications. They hint that the world we see is a filtered version of something vaster, an ocean of connected qualities, constantly rearranging. The grin of the cat, the spin of the neutron, the spark in your eyes when you remember something beautiful. They are all echoes of one pattern, glimpsed through different windows of attention. As we drift from this quiet corridor of curiosities, a question follows softly behind. If even the smallest pieces of matter can slip apart and reunite, what does that say about the unity of the larger universe? If separateness itself is just a passing illusion, then perhaps connection isn't the exception, it's the rule. From here, the story opens once more, toward the mystery of what happens when an observer isn't just watching the universe, but helping it decide what it will become. There is a moment in every experiment that feels almost sacred. The instruments hum, the air grows still, and then, click. A detector fires, a number appears on a screen, and suddenly the world has chosen. What was only probability a heartbeat ago becomes fact. A photon lands here, not there. A particle spins up, not down. A blur of possibilities folds itself into one clear outcome, as if the universe had finally whispered, "This one." That tiny transformation, invisible but absolute, lies at the heart of quantum mechanics. Before measurement, reality behaves like a fog, soft, uncertain, overlapping. After measurement, it hardens into a single point of truth. Something has changed, but no one truly agrees on what that something is. Does observation cause the universe to decide? Does it simply reveal what was already there, waiting? Or does nature herself collapse her own indecision without us? To grasp this softly, imagine a violin string stretched in silence. Before you touch it, it holds the potential for many notes, every pitch hiding within its tension. The moment you draw the bow, one sound emerges clear and undeniable, while all others fade back into quiet. The measurement problem is the same question played in physics instead of music. What draws the bow? What turns the spectrum of possibility into the melody of one event? In the early days of quantum theory, Niels Bohr and Werner Heisenberg proposed a view that became known, in formal language, as the Copenhagen interpretation. We can think of it instead as the idea that reality waits for attention. In their view, The act of measurement doesn't merely record a result, it creates it. Until something interacts with a quantum system in a meaningful way, that system exists in a kind of suspended story, a paragraph full of unfinished sentences. The observer, by asking a question, completes the grammar. The world answers in the only way it can, by choosing one word out of many. But not everyone was comfortable with that idea. Erwin Schrödinger imagined his famous cat, alive and dead, in its box until someone lifts the lid, precisely to show how absurd it felt. Surely, he thought, reality doesn't hinge on a pair of human eyes. There must be another explanation. And so, other interpretations blossomed, each trying to make sense of this quiet collapse. One of them, the many worlds interpretation, refuses to accept collapse at all. Instead, it says that every possibility continues, branching into countless parallel realities. The universe never chooses, it sings every verse of its song at once, and we, the listeners, hear only one harmony. In that view, the click of the detector doesn't eliminate other outcomes, it simply separates them. Somewhere, in another version of existence, the photon landed there instead of here, and another you is watching that result. Then there is a gentler idea, called objective collapse, which imagines that nature herself brings order to her possibilities. When a quantum system grows large or complex enough, when it crosses a certain threshold of being, its wave of uncertainty collapses on its own. No consciousness, no observer, just the quiet patience of the universe, deciding when to condense its fog into form. You might picture it as dew settling on grass at dawn. No one commands it, no one witnesses it, and yet it happens all the same. Each interpretation tries to soothe a different discomfort. The Copenhagen view gives importance to awareness. The many worlds view gives continuity to everything. The objective collapse view gives autonomy back to nature, and yet none can claim final truth. They are all stories told to make peace with the same mystery. Why the world, so fluid in potential, becomes so singular in experience. It's tempting to think of this process as something technical, but perhaps it's something intimate. Each observation is a kind of relationship. The measuring device, the particle, the observer, all of them enter a shared moment. And in that moment, something new exists that wasn't there before. Measurement isn't violence, it's contact. A brushstroke meeting the canvas, a raindrop touching the sea. The collapse, then, is not a fall, but a gathering. The universe folds its maybes into one reality, like hands clasping together in prayer. Every time you look at the world, whether it's through a telescope or a simple glance at your own reflection, something is resolved. The haze clears for a heartbeat, and the universe reveals one of its faces to you, and when you look away, the fog returns, carrying within it the next set of possibilities. If we follow this thought inward, it starts to sound less like physics and more like poetry. Perhaps all of existence is a conversation between certainty and uncertainty, awareness and possibility. You could think of reality as an unfinished painting that completes itself each time it's seen. When no one looks, the colours drift softly across the canvas, rearranging themselves in silence. When eyes open, the pigments settle, if only for a moment before the dream resumes. And maybe that's why we find paradoxes so beautiful. They remind us that certainty is not the natural state of things. It's a temporary pause in an internal dance. What we call the real is simply the version of the dance that our attention happens to illuminate. The rest continues quietly, elsewhere, unseen but not lost. Quantum physics, at its heart, is not a cold study of particles. It's a meditation on the act of becoming. Every flash on a detector, every click in the dark is a small birth, a possibility collapsing into a moment, a thought made tangible. In that sense, the measurement problem is not confined to laboratories. It's in every choice you make, every moment you decide to notice something instead of something else. The world before your glance is a blur. The world after is a single note, trembling in the air. When you next open your eyes in the morning and the first light fills the room, you are performing the same miracle. You are helping the universe choose which version of itself it will be today. The act is so ordinary, yet so profound, that we hardly recognize it for what it is: creation in slow motion. And so, we arrive at a question that even science hesitates to ask aloud. If observation truly helps shape reality, then what is it about us that makes observation possible? Is it the eyes, the instruments, the equations, or something quieter, something that dreams and wonders? As we drift further into the story, the path leads us toward this deeper riddle. What if awareness itself is part of the experiment, not an outsider taking notes, but a participant in the unfolding of the cosmos? Close your eyes for a moment and listen, not to any sound in particular, but to the quiet hum of awareness itself. Somewhere between the breath you take in and the one you release, something delicate is happening. The world becomes known. It's not light striking your eyes or vibrations touching your ears. It's the act of being aware of those things that transforms them from happenings into experience. And that, in a whisper, is the puzzle that has lingered at the edge of physics for nearly a century. Does consciousness merely watch reality unfold, or does it help write the script? When the founders of quantum theory first saw how the world behaves at its smallest scales, they didn't expect to stumble into questions that sounded philosophical, even spiritual. But the mathematics left them no choice. Every experiment seemed to say that measurement, observation, was necessary to make possibilities become real. And if that was true, what counted as an observer? Was it a machine recording a signal? A human looking at a screen? Or was awareness itself, the quiet presence behind the gaze, the final bridge between probability and fact? The physicist Eugene Wigner wrestled with this thought. He imagined his now famous thought experiment, Wigner's Friend, where one scientist performs a measurement inside a sealed lab while another waits outside, unaware of the result. If quantum rules apply to everything, then from the outside perspective, the entire lab, including the scientist, should remain in a cloud of superposed possibilities until the door is opened and the friend's result is seen. But if consciousness itself collapses the wave of potential, then the collapse would have already happened inside when the friend first became aware. It's a loop that spirals back on itself. Observer observing observer, awareness looking at awareness. The question no longer belongs to physics alone. It becomes a mirror held up to our own existence. What is consciousness really? Is it something we have, like a property that belongs to us? Or is it something we are, a field we momentarily illuminate? Wigner wasn't alone in wondering. The mathematician John von Neumann suggested that the chain of measurement, the sequence of things observing things, could, in principle, continue indefinitely. A detector measures a particle. A camera records the detector. A person sees the camera. But somewhere, he thought, the chain must end. At some level, the act of awareness must anchor the observation, stopping the infinite regress. In his equations, the symbols ended, but the question lingered. What or who performs the final observation? You can imagine this like a hall of mirrors stretching into the distance. Each mirror reflects another, each reflection slightly fainter, until somewhere in the depth, there must be a real eye to see it all. The trouble is, physics cannot find that eye. It can only describe the reflections. Consciousness slips through its fingers, leaving traces but never substance, like mist that evaporates the closer you try to hold it. Still, it's hard not to feel that awareness and reality are entwined. The universe, after all, is full of patterns that only become meaningful when recognized. Spirals of galaxies, rhythms of atoms, symmetry in equations. Perhaps the act of recognizing is not separate from what is recognized. When we measure something, we're not just seeing it. We are allowing a piece of the universe to notice itself. The gaze, in that sense, is two-way. If this sounds mystical, it needn't be. There is a quiet logic beneath it. Everything we call real is filtered through awareness. Even this sentence, black text on a glowing screen, is nothing more than patterns of light until it enters your mind. The physics that produced it is objective, but its meaning exists only in you. Awareness may not create the world, but it certainly completes it, turning raw existence into experience. Some physicists today still flirt gently with Wigner's idea. They don't claim that consciousness alone makes reality real, but they suspect it plays a role in how reality is partitioned. Like a conductor guiding an orchestra, awareness might help coordinate which version of the quantum symphony becomes audible at any given moment. Not by force, but by resonance. In this view, consciousness isn't an intruder in physics. It's part of the equation, even if it hides behind the symbols. The universe and awareness might be two sides of the same coin. Matter becoming aware of itself through living beings, and awareness giving matter its form through observation. The two weave together in a kind of dance, neither leading nor following for long. If we soften this even further, we could say that consciousness is the universe's way of listening to its own music. Each mind is an ear, each thought a resonance. When you watch the stars are not passive. They are, in that moment, being noticed into clarity. Their light travelled for billions of years waiting for a place to land, and that place is the small window of awareness behind your eyes. Philosophers have long wondered if awareness could exist without an object, if pure consciousness without content is possible. Physics asks the question in reverse: could an object exist without awareness? Quantum mechanics doesn't answer either way, but it reminds us that the two seem inseparable. Observation gives structure to the world, and awareness gives meaning to the observation. They may be reflections of one phenomenon, the cosmos experiencing itself from the inside. You might think of reality as a vast dream, but not in the sense of unreality. Dreams, after all, are vivid and self-consistent while they last. The dreaming universe is one that generates observers so it can see its own beauty, one that writes consciousness into its laws so that its stories can be known. Perhaps we are those dreams, fleeting yet crucial, the eyes of infinity opening and closing across time. And if that's true, then each moment of awareness is a small act of cosmic participation. Every time you look at the world and truly see it, the curve of a leaf, the shimmer of water, the pause before sleep, you're helping the universe complete a thought, the observer and the observed, forever meeting in that quiet exchange. As we follow this thread further, the questions begin to stretch beyond the human mind. If awareness is woven into reality, what happens to it when the body dies? When the observer ends, does the observation go on? Does consciousness find another branch to inhabit, another path to continue the story? Our next step explores that strange horizon, where identity, survival, and the quantum world collide. A thought experiment that dares to imagine what it would mean to never stop waking up. There's a strange quiet that settles whenever people talk about immortality. Not the shining, triumphant kind from stories, but the lonely, mathematical kind whispered about in physics. The kind that sits at the crossroads of probability and consciousness. It's called the quantum suicide thought experiment, though the name hides something far more reflective than morbid. It isn't about destruction, it's about what it might mean if awareness could never stop being aware. The idea was proposed not by mystics, but by physicists trying to make sense of the many worlds interpretation of quantum mechanics. In that view, every possible outcome of an event actually happens, but in separate branches of reality. The universe doesn't choose, it multiplies. Each moment of uncertainty splits the cosmos into parallel versions, each carrying on with its own version of the story. Most of us hear that and picture a branching tree of worlds, stretching into infinity, some familiar, some forever out of reach. The thought experiment asks a haunting question. If the universe keeps splitting, and if every version of you continues in one of those branches, then from your own perspective, the perspective of awareness, could you ever actually cease to exist? Imagine a scientist in a quiet room with a simple device. It's designed to measure a quantum event, something perfectly balanced between two outcomes, say, a particle's spin that can be up or down. If it's up, a light flashes and the scientist continues on unharmed. If it's down, the machine does something fatal. In a single universe, that would be the end of the story. But in the many worlds view, both results occur. In one branch, the scientist dies. In another, they live. From the perspective of outside observers, the probabilities are clear, 50-50. But from the inside, from the scientist's own awareness, what happens? In the thought experiment, the scientist always wakes up in the branch where they survived. The branches where awareness ends fade from their perspective completely. To them, every trial ends the same way. Another breath, another heartbeat, another click of the machine followed by silence and survival. From their point of view, death never arrives. The world keeps rearranging itself to preserve the viewpoint of consciousness. It's a chilling, elegant paradox. The idea that awareness might always find itself in the surviving branches, continuing endlessly, while the world outside continues to split into versions where others grieve and move on. Survival, here, is not a reward, it's a loop. An unbreakable narrative where the protagonist can never read the final line. To describe this in softer language, think of it as a story that refuses to end because its narrator can never step out of the telling. Every possible ending is written somewhere, but the act of awareness, the act of reading, keeps turning the page. You can never see the chapter where you're no longer present. From your perspective, consciousness is always now, always continuing. It sounds like a miracle, but it's not the kind that brings peace. Imagine waking again and again in countless versions of reality, each time carrying the memory of having survived. Others fade away, the world resets, time and identity stretch on, without pause. The thought is meant not to promise immortality, but to test what immortality might actually mean, and whether endless continuation could still be called life at all. Some have criticised the idea, pointing out that it can never be tested, that it blurs the line between physics and philosophy, and they're right. It isn't an experiment anyone would or should perform. It's a mirror for the mind, showing us what happens when we push our theories of observation and identity to their edge. The mirror doesn't tell us truth, it reveals our reflection. Perhaps the most unsettling part is how naturally the logic flows. If every outcome exists somewhere, and awareness follows the path of survival by definition, then subjective experience, what it feels like to be alive, never encounters its own absence. From within the dream, you never wake. And yet, maybe the flaw is in thinking of awareness as a traveller that moves through worlds. Maybe awareness is the light itself, not the thing being carried. When the bulb breaks, the room goes dark, but the light isn't lost. It was never confined to the bulb. In that sense, what continues is not the person, but the pattern, the glow that once animated a body. The many worlds theory might be less about eternal survival and more about eternal transformation, the endless recycling of possibilities. You could also imagine this as the sea of existence itself, forever rearranging its waves. From the point of view of the water, nothing ever dies. Each ripple simply blends into others, changing shape, never vanishing. But from the point of view of the ripple, it feels like an ending. The difference lies only in perspective. Quantum suicide, when spoken gently, is less a story about death than about how tightly consciousness clings to continuity. It asks us to wonder what awareness really is, an individual stream or the ocean of all streams combined. The experiment's strange promise of endless waking becomes, in another light, a metaphor for the universe's own persistence. Just as energy cannot be destroyed, maybe awareness cannot simply end. It can only change form, dissolve, merge, or reappear in new patterns of being. There's a quiet melancholy to that idea, because it means that the self, this small collection of memories and hopes, might not be eternal after all. The continuity we feel may belong to something larger. Awareness itself, indifferent to the forms it takes. Each life, then, becomes a brief crystallization of perception, a wave that rises, glimmers, and falls back into the sea. When we step back, the thought experiment transforms from a puzzle into a meditation. It's not about tempting fate, but about recognizing that consciousness, whatever it is, doesn't easily fit inside our definitions of beginning and end. Whether we imagine countless branches or a single unfolding whole, awareness seems to be the thread that runs through them all. And perhaps that's enough. To know that you are a witness in a universe that cannot help but keep creating witnesses. That every breath you take is a continuation of the same quiet miracle that began before you and will outlast you in forms you'll never see. The physicist Hugh Everett, who first proposed the many worlds idea, once said he was comforted by the thought that somewhere, in another branch, every possibility finds life. It's a gentle way to end a frightening theory, with compassion for all the versions of reality we'll never meet. Maybe that's what the quantum suicide story is trying to tell us, that existence, no matter how fragmented, still finds a way to keep its light on somewhere. If we follow this thought just a bit further, we find ourselves standing before a hall of mirrors, each reflection another you, another world, another thread of awareness still burning quietly in the dark. What does it mean to be one flame among billions? To be part of a pattern that never truly ends? Our journey now drifts toward that question, the puzzle of identity itself, and what it means when every self is one of many selves of the same eternal observer. Imagine a candle burning in the dark. Its flame trembles, steady but alive, and in every flicker it splits into reflections, on glass, on walls, in the faint shimmer of your eyes. Each reflection seems to be its own flame, separate and glowing, but they are all born of the same light. This is what identity begins to look like through the lens of quantum thought, one awareness, seen from countless angles, each convinced it burns alone. The quantum world tells us that reality may not be singular. Every measurement, every choice, every chance event unfolds into many versions, like branches of a vast growing tree. You walk through one path, feel its leaves under your hands, while countless other versions of you walk among the others, each carrying a slightly different story. It's a breathtaking idea, the notion that all possibilities exist somewhere, all happening at once, all equally real. But inside that beauty lives a quieter question. If every version of you exists, which one are you? You might think that consciousness moves along one timeline like a bead sliding on a string. But quantum theory suggests that the string itself may fray into countless strands, each carrying a slightly different melody of experience. In one, you turned left instead of right. In another, you didn't take that job, or that flight, or that chance. Yet in each, you are certain that you are you. Awareness doesn't feel divided. It feels whole, even while the universe unfolds into its many selves. Some physicists call this the observer selection effect, but we can speak of it more softly. Awareness finds itself wherever it continues. In all the countless possibilities, you awaken in the one that fits the shape of your memory. It's not that you leap between universes, it's that your story flows through the path that still carries you forward. The other versions exist, but they no longer feel like yours. You can picture this as a forest at night. Every path stretches into shadows, branching and weaving endlessly. You carry a lantern, your awareness, and wherever you walk, the forest around you lights up. The paths you don't choose remain dark, but they are still there, unseen, waiting. You experience one illuminated journey, yet the forest holds them all. If we follow this thought a little further, it begins to touch something tender: identity itself. Who are you, really? Are you the sum of your memories, the pattern of your thoughts, the echo of every choice you've made? Or are you something deeper, the quiet awareness watching all those changes come and go, unchanged beneath the flow? In this gentle framework, the self becomes less of a fixed point and more of a continuity, like a melody that keeps playing even as the instruments change. Imagine billions of candle flames scattered across the dark, each flickering in its own rhythm. Every flame believes it's alone, but if you step back far enough, you can see the pattern they form together, the constellation of one great light spread thin. Perhaps that's what consciousness truly is. Not a single flame, but the total glow of all of them. Each life, each version, each thought is a shimmer of that same awareness, localized just enough to feel unique. The philosopher William James once called consciousness a stream, but maybe it's more like an ocean, full of waves that think they're separate rivers. You, sitting here listening to this story, are one of those waves, a crest rising briefly, aware of itself before merging back into the sea. When we think of quantum branching, of many worlds diverging, it might be that the sea is exploring every possible shape of itself, not as confusion, but as curiosity. It's tempting to imagine that somewhere, another version of you is listening to these same words, perhaps at a slightly different hour, with a different set of thoughts trailing behind. You might never meet that version, yet together you form something whole, the total map of how awareness unfolds across all its possible lives. The idea doesn't need to be literal to be beautiful. Even within one lifetime, you've been many selves already. The child you were, the dreamer, the learner, the one who laughed too loud, the one who grew quiet with time. Each of them feels complete, but none of them alone define you. Identity, like reality, is a branching story that keeps rewriting its own opening line. This perspective softens the fear of endings. If consciousness is not bound to a single thread, then death may not be the opposite of life. It may be the continuation of awareness along another path, another rhythm. Not in a supernatural sense, but in the same way that music lingers after the note fades. The song is never gone. It simply changes instruments. There's also humility in this view. It suggests that your choices, while personal, are also universal. Every act of kindness, every thought of compassion, sends ripples not only through this world, but through the pattern of all possible worlds, enriching the field of awareness itself. You may never see the echoes, but somewhere, in one of those infinite branches, they bloom. And if every observer carries a fragment of the same underlying awareness, then perhaps individuality is not a boundary but a lens, a way for the cosmos to study itself from different angles. Through your eyes, the universe experiences what it's like to be you. Through another's eyes, it feels something different. Together, these perspectives create the full picture, an ever-expanding self, dreaming itself in countless forms. Somewhere deep in that realization lies peace. You're not lost among infinite versions. You're the awareness that watches them all. The flame, the forest, the ocean. They're metaphors of the same gentle truth, that consciousness, like the universe, refuses to be confined. It explores every possibility not to escape itself, but to know itself. As we drift towards sleep, it's worth lingering on that image. Billions of candle flames flickering in the dark, each one carrying the same invisible spark. You, me, the stars above, and the smallest particles we've spent this whole journey exploring. They're all part of one vast, self-aware pattern. When the flame you call yourself dims, the light doesn't vanish. It flows onward, joining the others, illuminating new corners of possibility. And that brings us gently to the next horizon, where the mysteries of consciousness meet the mysteries of gravity and time. If awareness can influence quantum events, could it also play a role in the way the cosmos itself remembers? The trail of thought now leads us toward the greatest paradox of all, a place where even light can't escape, yet nothing is ever truly lost. Imagine drifting through the night sky, past stars that shimmer like slow thoughts, past the soft spirals of galaxies glowing at the edges of darkness. Far ahead, you see something that looks like an absence of light, a hole carved into the fabric of space itself. Around it, everything seems to fall inward. Dust, starlight, even time. This is a black hole. Not so much an object as a silence, a place where gravity has folded space and time so tightly together that nothing can escape its pull. Even light, the fastest thing we know, slows, bends and vanishes beyond its invisible edge. The idea of a black hole began as pure mathematics, a side effect of Einstein's equations describing how gravity curves space-time. Those equations allow, in theory, a point of collapse so dense that the normal rules of physics break down. For decades, it was treated as a strange curiosity, something that might exist only on paper. But the universe had other plans. Astronomers began to find stars orbiting invisible companions, moving too fast, too close, as if tethered to something immensely heavy yet unseen. Eventually, telescopes caught the glow of matter spiraling into these unseen centers, heating up as it fell, screaming across the electromagnetic spectrum before crossing a threshold beyond which no signal could return. That boundary is called the event horizon, but you can think of it as the edge of knowable reality. What crosses it doesn't just disappear, it becomes unknowable to us, cut off from the universe we inhabit. Inside, the equations predict a singularity, a place of infinite density and zero volume, where space-time folds into itself like a clenched fist. But infinity isn't a place you can point to. It's a confession that our understanding stops there. For most of the 20th century, black holes were cosmic endpoints, perfect destroyers. Matter falls in, information is lost, and the story ends. Then, in the 1970s, Stephen Hawking discovered something extraordinary. When quantum mechanics is allowed to whisper its corrections into Einstein's elegant geometry, the picture changes. The vacuum around a black hole isn't empty. It seethes with pairs of particles briefly appearing and vanishing, a quantum foam of existence and non-existence. Normally these pairs meet and cancel each other out, but near the event horizon, one partner can fall in while the other escapes. To a distant observer, that escape looks like a faint, steady glow of radiation. This Hawking radiation means black holes aren't perfectly black after all. They can lose energy, slowly evaporating over unimaginable spans of time. It's a revelation that turned the physics world upside down, because if a black hole can evaporate, the information about what fell inside should somehow vanish too. And according to quantum theory, that cannot happen. Information, in the deepest sense, must always be preserved. The universe is not allowed to forget. Here lies the heart of the paradox. General relativity, the grand theory of the cosmic stage, says black holes erase details completely. Quantum mechanics, the precise language of the microscopic, insist that every detail must remain encoded somewhere. Both are breathtakingly successful, yet together they refuse to agree. To imagine this more softly, think of a great library that catches fire. Every book, every page, is swallowed by the flames. To us, the stories are gone forever. But in quantum law, the ashes and the smoke still hold the patterns of those lost words, scrambled, scattered, almost unreadable, yet still present in principle. The universe, it seems, keeps every draft. Some physicists believe that the missing information isn't truly lost but woven into the faint radiation escaping the black hole, a kind of cosmic whisper carrying the memory of everything that once fell in. Others imagine that the information might be stored on the surface of the event horizon itself, encoded in tiny quantum ripples. This idea, known as the holographic principle, suggests that all the details of what lies inside are somehow projected on the outer boundary, like a three-dimensional story written on a two-dimensional page. Even without the equations, it's a haunting image, a black hole as both tomb and archive, burning its pages while still keeping the story. The closer we look, the more it feels like the universe is refusing to let go of anything, not even the things that seem most utterly gone. And maybe there's something deeply human in that. We too have horizons, the limits beyond which memory fades, or words fail, or emotions slip into silence. Yet, like the universe, we rarely forget completely. Every experience leaves an imprint, however faint, somewhere in the fabric of who we are. Our minds, like the cosmos, store everything in patterns we can't always retrieve but never fully erase. There's also a kind of forgiveness in this paradox. The black hole, once imagined as the destroyer of all, becomes something gentler, a keeper of secrets. It doesn't annihilate the universe's history, it just hides it in ways we don't yet understand. The darkness is not absence, but mystery condensed. To scientists, solving this puzzle is more than curiosity. It's a key to uniting quantum mechanics and gravity into one grand theory. Somewhere inside the paradox lies a truth that could reveal how space-time itself arises from information, how matter and energy are just patterns of knowledge written into the void. To dream of that solution is to glimpse the architecture of reality. Not matter, not motion, but meaning. And if that is so, then perhaps the universe doesn't merely exist. It remembers. Every photon, every particle, every heartbeat and thought is part of an infinite ledger, written and rewritten in the shifting light of time. What we lose may never truly be lost, only transformed, folded back into the quiet pages of the cosmos. So the black hole, instead of being an end, becomes a promise that nothing vanishes without leaving a trace, that every moment contributes to the story even after it falls beyond our sight. The faint glow of hawking radiation is like the whisper of that promise, a soft shimmer in the darkness saying, "I'm still here." As we drift deeper into this realization, another layer of mystery begins to unfold. If the universe records everything, then what does it mean to say that information is stored on a surface, or that space itself might be an illusion made of data? The trail of thought now leads us toward those strange ideas, the holographic universe, firewalls of light, and hidden codes that might be the true substance of reality itself. Imagine you're standing before a black hole, though of course you can never truly stand before one. The light bends so sharply around it that even your sense of direction begins to blur. The stars behind it smear into arcs, as if painted by a trembling hand. There is no sound, no air, only the deep hush of space. You watch as matter falls inward, spiraling like petals caught in a whirlpool. The scene is hauntingly beautiful, destruction shaped like grace. But the closer you look, the more the story begins to change. What if, instead of erasing what it swallows, the black hole is secretly preserving everything, writing it into the very surface of its darkness? That idea, the holographic principle, has become one of the most startling insights in modern physics. It was born from a puzzle, the same one we explored before. How can information survive if it falls into a place that seems to forget everything? The answer, it turns out, may be that the information never truly goes inside. Instead, it stays imprinted on the boundary, the event horizon itself, like a cosmic archive so vast that it holds the story of every particle that has ever crossed its edge. To imagine it softly, picture a three-dimensional sculpture that, when lit from the right angle, cast a two-dimensional shadow revealing its full shape. Or think of a pop-up book flattened closed. The story's still there, just waiting for light to lift it back into form. In this view, our universe might work the same way. Everything we experience in 3 dimensions could be a projection, a kind of hologram woven from information stored on a distant surface. It's a strange comfort, the thought that reality, however complex, might simply be the universe remembering itself. Each atom, each star, each heartbeat would be a line in the great script of existence, encoded not in matter, but in information. You could say that space itself is a language, and every event is a sentence in that language, written on the thin, invisible skin of reality. But as always, nature refuses to let the story end without a twist. Around the same time this holographic idea took hold, a new paradox emerged, one that questioned what really happens at the edge of a black hole. According to Einstein's relativity, the boundary should feel smooth to someone falling in. They would cross it without noticing, drifting silently toward the singularity. Yet, according to quantum mechanics, all the information from what falls in must somehow be preserved there, at the surface. Those two views cannot both be true. Something must give. Some physicists proposed a daring idea. What if the event horizon isn't smooth at all? What if, instead of passing through peacefully, an infalling traveller would be burned instantly by a wall of unimaginable energy, a firewall of pure information? It's a shocking thought, almost violent in contrast to the tranquil beauty we imagine. The equation suggests that to preserve quantum information, the horizon must become a barrier of light, a boundary that protects the universe's memory from contradiction. To soften that image, you might think of the firewall not as destruction, but as transformation. The matter that falls in doesn't die. It translates. Like paper fed into a bright scanner, its details are converted into patterns of light, its data preserved in a new language. To the outside universe, the information remains encoded in the glow of Hawking radiation, spread thin across time but never truly lost. The black hole, then, is less a graveyard and more a translator between forms of being. These ideas are more than theories. They're glimpses of how the universe might actually store its secrets. Physicists like Leonard Susskind and Juan Maldatina found hints that the laws of gravity in a higher dimensional space could be exactly equivalent to quantum laws on a lower dimensional surface. 2 completely different languages telling the same story. It's as if the universe comes with subtitles written in another dimension. To think of it in poetic terms, reality may be a mirror that reflects itself across dimensions. What you see as space and depth might be the echo of something far simpler, flattened but complete. A cosmic photograph so precise that every detail of your life, every flicker of starlight, is captured within its grain. Even in laboratories, small echoes of these ideas have begun to appear. Scientists create analog black holes using ultra-cold atoms and light waves, tiny universes where horizons form and vanish in miniature. In those controlled experiments, they can see faint signs of Hawking-like radiation, as if the laws of information and gravity are rehearsing their cosmic dance on a smaller stage. Each of these experiments is a gentle reminder that the great paradoxes of the cosmos are not out of reach. They are mirrored in every whisper of physics around us. The more we explore, the clearer it becomes that information may be the most fundamental ingredient of the universe. Not atoms, not energy, but the pattern that gives them meaning. If so, then everything that exists is a kind of story, an arrangement of information woven into the fabric of space. You, sitting here, are not a collection of particles, but a narrative written in the code of reality itself. And if that's true, then perhaps death, loss, and disappearance are not the vanishing we imagine, but a kind of rearrangement. The data of your being, your thoughts, your experiences, your laughter, may disperse, but it never leaves the script. The universe keeps every page, even the ones that fade from memory. It's strange to realise that the deepest questions in physics sound almost like the oldest human questions. What happens when we die? Is anything truly forgotten? Does meaning survive change? The holographic universe whispers a quiet answer, that maybe everything that ever was still exists folded into the shining surface of space, waiting to be read again when the light is right. If we follow that light a little further, we begin to see a pattern that stretches beyond black holes and into the heart of reality itself. Every paradox we've met so far, the duality of waves and particles, the branching of observers, the collapse of possibility, the whispers of entanglement, has been pointing toward the same quiet truth. Perhaps the universe isn't made of things at all. Perhaps it's made of relationships, of meanings waiting to take shape. The path ahead leads toward that final reflection. What if paradoxes aren't mistakes but messages? What if they're the universe's way of telling us that our language is too small for what it's trying to say? The story now turns toward that possibility, that confusion is not the enemy of understanding, but the doorway to a new kind of clarity. If you've ever tried to describe a dream the morning after, you know how fragile truth can feel when you put it into words. You reach for language, but it slips through your fingers. Something important, something vivid and alive, stays just beyond what speech can hold. Science often feels the same way. The deeper we look into the universe, the more our equations resemble poetry we don't yet understand. The paradoxes we've met along this journey, the double life of particles, the strange survival of information, the two-way flow of time, are not mistakes in the story. They are its punctuation marks, hints that we've been reading the universe in translation. Every great revolution in physics began with such discomfort. Newton saw an apple fall and imagined invisible forces stretching between stars. Einstein looked at the speed of light and realized time itself must bend. Planck, Heisenberg, Schrödinger, all of them stumbled into paradox and followed it to revelation. It's a pattern as old as curiosity itself. Confusion first, clarity later. The universe teaches by contradiction, as if to remind us that certainty is a brittle thing. Perhaps that's why so many scientists speak of beauty when they talk about their work. Beauty is not just decoration. It's the feeling that arises when complexity hides a deeper simplicity, when 100 questions begin to rhyme with a single answer. Yet we're not there yet. The equations we have today, quantum mechanics on one side, relativity on the other, speak two dialects that refuse to blend. One describes the very large, the other the very small, and somewhere between them lies the unspoken sentence that could unite them both. Some believe that sentence will come from mathematics, a new symmetry that quietly bridges gravity and quantum fields. Others believe it will come from a more radical shift, from realizing that reality itself may not be made of matter or energy at all, but of information, of relationships, of meaning. We've already seen how the holographic universe turns space into a kind of data field. Maybe that's not an exception. Maybe it's the rule. To imagine this softly, think of the universe as a story written not in ink but in patterns. The characters, atoms, galaxies, you, are the words that appear when relationships form. Reality, then, is the grammar of connection, and physics is our attempt to learn its syntax. We may have spent centuries studying the letters, but only now are we beginning to sense the poetry hiding between them. Even time, that most fundamental rhythm, might just be one chapter in a language of meaning we haven't yet learned to read. Quantum mechanics shows us that events don't simply unfold in a single line. They shimmer with probabilities, correlations, and feedback between past and future. Maybe causality itself is a kind of sentence structure, the way the universe links ideas into coherent thought. If that sounds abstract, imagine it this way. Every particle interaction is a word, every field equation, a phrase, every force, a metaphor binding ideas together. And you You are the moment when the story reads itself aloud. Awareness isn't separate from the text. It's part of the language, the sound that gives it life. This view may feel poetic, but it's also quietly practical. When scientists struggle to merge quantum theory and relativity, they're really trying to find a language where both can coexist without contradiction. Each new discovery, dark energy, entanglement, black hole information, adds another piece to the vocabulary. We are learning, letter by letter, how the universe writes. What might that final language look like? Perhaps it won't mention particles or forces at all. Perhaps it will describe relationships so subtle that space and time themselves emerge as side effects, like melody emerging from the vibration of strings. Some physicists suspect that even space-time might be a derived concept, a network woven from the links between bits of information, a tapestry of correlations rather than coordinates. To put it simply, the universe may not be made of things. It may be made of meanings. And meanings, like melodies, can't exist in isolation. They require context, harmony, relation. When you think of yourself, you might picture a single mind in a single body, but you're also a node in countless connections, memories, relationships, atoms borrowed from stars. You're not an isolated object. You're a pattern of meaning sustained by everything else. There's something freeing about that realization. It means that understanding the universe might not mean conquering it or reducing it to smaller pieces. It might mean learning to listen, to recognize the rhythms that have been playing all along. Science, in this sense, isn't about control. It's about translation. We're trying to translate the language of being into human understanding, and paradoxes are the hints that we're close but not quite fluent. If we follow this thought gently, the next revolution in physics may not begin with new machines or even new mathematics, but with a new kind of humility, a willingness to accept that truth might feel more like music than machinery, that the laws of nature are not commands but harmonies, and that comprehension may arrive as stillness rather than explanation. The great physicist John Wheeler once wrote, "It from bit," meaning every it, every particle, every field, everything is born from information, from bits of yes or no, being or not being. But what if information itself is just another word for awareness? Perhaps the cosmos is not a machine that produces data, but a mind that creates understanding. Every photon exchanged, every atom bonded, every human thought, all parts of the same sentence, written and rewritten endlessly across the sky. To live in such a universe is to be both reader and author. Every choice you make, every question you ask, every quiet moment of wonder contributes a new word to the story. You are part of the language, part of the grammar of existence. And though we haven't yet learned to read the whole text, we can feel its rhythm every time we look up and sense the vast, calm intelligence behind it all. The universe has been speaking to us in the only way it can, through paradox, through pattern, through beauty. And maybe our task isn't to solve those paradoxes, but to learn to hear what they're saying. They are not riddles to conquer, they are bridges to understanding. They whisper, "You're close. Keep listening." As we approach the end of our journey, one final thought drifts softly forward. If awareness and meaning are truly the fabric of reality, then the universe might not just be something we watch, it might be something that watches back. And in that quiet exchange between observer and observed, maybe existence finds its purpose. You've spent this whole journey peering into the universe, tracing its riddles from atoms to galaxies, from quantum whispers to cosmic horizons. But somewhere along the way, the direction of that gaze begins to blur. You start to sense that while you've been watching the universe, it's been watching you back, not through eyes, but through presence, through the simple fact that awareness exists within it at all. There's a quiet symmetry here. You, a small being made of borrowed atoms, are composed of the same matter and energy that fills the stars. The particles in your body were forged in ancient suns, and before that, in the silence that followed the Big Bang. The hydrogen in your breath, the carbon in your bones, the iron that gives your blood its colour, all once belonged to places far older than memory. So when you look up at the night sky and feel something looking back, it isn't imagination, it's recognition. Every law of physics that governs the cosmos also governs you. The quantum rules that let photons dance and electrons hum are the same rules that let your neurons fire, your heart beat, your thoughts form. You're not a visitor here. You're an expression of the same equation, a local curvature in the fabric of reality where the universe has become conscious of itself. The great paradox, perhaps the gentlest of all, is that we search for meaning in the universe, not realizing that meaning is what the universe becomes when it learns to look inward. Every act of curiosity, every quiet moment of wonder, is the cosmos experiencing itself from within. Awareness is not an outsider observing the universe. It is the universe folding back to see its own reflection. This perspective transforms the grand scientific story into something intimate. The wave that collapses when you observe it, the entanglement that links distant particles, the information preserved on the skin of a black hole, all of it reflects a deeper truth: participation. The universe doesn't unfold for you, it unfolds with you. Every question you ask reshapes the story slightly, like ripples meeting in a pond. Every act of perception is a collaboration between mind and matter, a duet written in the language of existence. To put it softly, you are both the reader and the page. The act of looking writes new sentences into the story. When you measure light, light tells you who you are. When you breathe, the universe continues its rhythm through you. When you fall asleep, your dreams are the small-scale version of cosmic creation. Reality is built from observation, memory, and imagination, each as delicate and transient as a nebula dissolving in starlight. Even the paradoxes that once felt cold and technical now sound like lullabies. The uncertainty principle isn't chaos, it's permission. It says that possibility is never fully closed, that there will always be mystery enough to sustain curiosity. Superposition is not confusion, it's generosity, a reminder that reality contains more than one truth at once. Entanglement is not trickery, it's the quiet signature of unity, a cosmic reassurance that nothing, not even light years of distance, can truly separate what was once connected. And perhaps that's the lesson hidden beneath all the equations. The universe is not a machine of isolation, but a tapestry of intimacy. From the particles that dance in quantum fields to the galaxies spiraling across the dark, everything is bound by relationship. Even gravity, the force that keeps planets in orbit and your feet on the ground, is just another form of attraction, a conversation between masses saying, "I feel you." In this light, science and wonder are no longer opposites. They are the same gesture seen from two perspectives, the mind measuring and the heart marvelling. To understand the universe deeply is to love it more completely, not with sentimentality but with reverence. The equations are not just numbers, they are poetry written in the script of being. If you let yourself drift a little further into this thought, a gentler realization begins to rise. Maybe the universe does not have meaning in the way we expect. Maybe it is meaning. Continuous, unfolding, learning, dreaming. It doesn't need a destination because it is always arriving. Each life, each thought, each observation is one more way the cosmos discovers itself. And what of you, the listener, the quiet traveller of these ideas? You're not small in this story. You're precisely the scale at which the infinite learns to speak softly. Your awareness is the lens through which the vast becomes personal. Every question you hold is a bridge between starlight and thought, between the unknown and the known. It might be comforting to realize that even your uncertainty belongs. When you wonder about your place in the universe, that wondering is your place. The confusion is part of the harmony. The paradoxes we've explored are not obstacles to understanding. They are the very shape of understanding itself. They remind us that truth is not a fixed point but a living rhythm, always changing, always expanding to include more of what it once excluded. As this story nears its end, it feels right to imagine the universe not as something far away, but as something breathing with you now. Every pulse of your heart is echoed in the slow expansion of space. Every spark of thought is a flicker of the same quantum field that births galaxies. You are, in every sense, the universe learning to observe itself, quietly, curiously, endlessly. And when you close your eyes tonight, know that you're not falling out of awareness. You're returning to it. Sleep is the small rehearsal of cosmic rest, where the observer dissolves back into the observed, and the line between self and everything else fades to nothing. The stars will still burn, the photons will still travel, the questions will still hum through space. You can rest, because the universe will keep wondering for you. So, sleep well, traveller of light and thought. You've wandered far, from uncertainty to unity, from paradox to peace. The cosmos will continue its quiet dialogue, written in waves and whispers, and when you awaken again, you'll still be part of the same great experiment, the one where existence looks back at itself and smiles.